So okay, then I think we should start the class now. My slide is visible to all. Can anyone just comment?
Yes, sir.
Yes, sir.
Yes, sir.
Great. So due to Christmas and so many other things with you all, and of course with me also, we could not meet in last 8 to 10 days, and last two classes are remaining, and these two classes are very important because up to this point, up to this particular point, whatever, one second. Yes, so up to this point, whatever I have shared with you was for doing the statistics, finding out more insights out of it, and seeing the data from different angles. It was also about to see what kind of distribution our data will fall, and if we know what kind of distribution it is falling, we can apply the relative formula for the from that, and we can make predictions out of it. But uh, but the last two class are special because here now we are going to make real time decision. I would not say real time, but real life decision, because here we will be actually giving the values in a particular range by which we can make policy, by which we can make some scientific advancement and other things which will really make some change. Up to this point, I can say that we were doing in-depth analysis and of course some conclusion also, some decision making also. But with statistical estimation and hypothesis testing, we can very well make some decisions out of it. So we'll start. So I hope normal distribution you all remember. We have seen it in great details that time. We have seen various formulas and all other things. Now we will see some other aspects of normal distribution. So here I will start with percentage points to the normal distribution. Okay, we will first we'll start with percentage points to the normal distribution. I'll just read the line what I have wrote, and you just also read and try to understand. So first thing is this: in many problems of applied interest. Okay, here you can see I wrote applied interest because I told you last two classes are when we are actually going to apply. In many problems of applied interest, we will be working with many quantities which have the standard normal distribution. Right, I told you that normal distribution is actually distribution of nature. Most of the times you will be encountering this distribution only. And what we will do is that first, for this standard normal distribution, we will devise one labeling mechanism. Okay, we will devise one labeling system. So what we will do is that by now we were seeing that okay, with this much is the percentage points, this is the Z value, or this is for this Z value, this is the percentage points. But now we will deal with the level of significance also. Okay, so here you can see, here I have given one particular word. It is a Greek word. It is known as alpha. No, we call it alpha. We call it alpha. So we will denote level of significance by alpha. We will denote level of significance by alpha. And when I say alpha, it means to say proportion of data in standard normal distribution. Okay, level of significance or proportion of data in standard normal distribution we will denote by alpha. So we always take alpha by 2. This you will come to know why we are taking alpha by 2, because we want to give range. Okay, in subsequent slides it will be clear to you why we are taking alpha by 2. Okay, so suppose alpha is my level of significance. Alpha can be any numerical value. Okay, can be any numerical value between 0 to 1. So when I am putting it in a standard normal distribution, we will use Z alpha by 2. Okay, we will use Z alpha by 2 to signify the Z value of a standard normal distribution, which has to its right. This thing you have to keep in mind, which has to its right a fraction of alpha by 2 of the data. Okay, so suppose if this fraction is alpha by 2, This will be of course 1 minus alpha by 2 because the total area is 1. I hope you remember this. In our table A3, I told you that when particular value is this one, remaining will be 1 minus this value, whatever that value may be. So if I am saying this is alpha by 2, this proportion is alpha by 2. Obviously this will be z alpha by 2 because here we plot z scores, right? Here we plot z scores. So naturally this will be 1 minus alpha by 2. Okay, so I hope up to this point it is clear to you. We call alpha as level of significance, and uh, we always take alpha in two parts. Alpha by 2 on the right, alpha by 2 on the left. But in standard normal distribution, we will say to its right because overall we know that it is 1. So 1 minus alpha by 2 will be the remaining proportion. Okay, I hope this labeling system is clear to you by now. Now I'll give you one example. So suppose I want to know that at 5% confidence, at 5% error with 95% confidence, what will be my z value? Okay, so if it is 5, I will divide 5 by 100. Okay, I will divide 5 by 100, so it will be 0.05, right? 0.05. So this is my alpha. Okay, what I'm trying to do is that I want to leave 5% this side and I want to be 95% sure of something. I want to be 95% sure of something. So this is alpha. Alpha is my 0.05. But I have to see half. I have to do half of it. I told you already that we will do half. This you will understand slowly in the subsequent slide why I am doing alpha by 2. So I will do alpha by 2 of it. I will do alpha by 2 of it. So of course 0.05 divided by 2 will be 0.025. Now again I will go to my table A3, what I have shared with you earlier also. I will go to table A3 and here you can see I have to see 0.025. 0.025. So it will come somewhere here. 0.0250. You can see here it is related to 1.96. 0.025. So my alpha is 1.96. I am not taking minus symbol now because anyway we have divided in 2. So for this side it will be plus, for the other side it will be minus. Minus 1.96 plus 1.96. So I am only denoting the numerical value of 1.96. So I hope this is clear to you that when I am taking a particular level of significance alpha, first I will divide it by 2 and corresponding to that proportion I will see the z value. Okay, I'll just repeat. First we will take alpha. It will be a certain proportion or percentage. Then I will divide it by 2 and whatever value comes in respect of that value I will see my z value. Okay, I will see my z value. So in this case, how I will write it? What will be the denotation? Z subscript alpha by 2. My alpha by 2 was 0.025. So I will replace alpha by 2 with 0.025. Z 0.025. And in this case we found out as 1.96. So Z 0.025 is equals to 1.96. Okay. So I hope up to this point it is clear to you. And also I am not doing anything right now here. I will come to subsequent slide. So when I am taking 2.5% only, naturally the remaining will be 97.5%. Okay, if now I am taking 2.5%, remaining will be 97.5 only. Now I have created one table for different values. So suppose my alpha is 0.20. So of course my 1 minus alpha will be 0.800. So corresponding to 0.800, my z will be 0.84 from table A3. Okay, from table A3. Now I did half of it. So 0.20 divided by 2, that is 0.10. Then again I have deducted the 0.10 from 1. So it is 0.900. And corresponding to 0.900, my alpha by 2 will be 1.28. This is also from A by 3. So this is in the proportional line and this is in the Z table. You can see here we have, I have already mentioned you. So here you can see 0.800. I will take the smaller one, say 0.7995. Here you can see where I am making a circle. 0.7995. So it is similar, it is almost equal to 0.800. So corresponding to that, my value is 0.84. So I have taken 0.84 here. Here you can see Z alpha. Similarly, you can see for other values also. Okay, anyway, I have shared with this you. You just see whether all the values are correct or not. If some discrepancy is there, let me know. Now, how I can show it? Suppose if I left 0.005 minus 0.005, the z value will be 2.57. If it is 0.01, it is 2.33. 0.025 already I have showed you, it is 1.96, right? For 0.05 it is 1.64, and for 0.10 that is 10%, 1.28. So for corresponding level of significance, this line, this diagonal line is alpha. This is level of significance. For all corresponding level of significances, we have this Z score. We have this Z score. So I hope this is clear to you, that we will see on the right side. If I am seeing this one, this will be, I'll do 1 minus alpha. If I am seeing this one I'll do 1 minus alpha. Okay, so slowly I will come to understand that how much confidence I am having while reporting my result. Okay, how much confidence I am having while reporting my result, whether it is in research paper or any statistical estimation or any report which we do. Okay, so table A3 I have already explained to you all these things, how to see table A3, and Praveen Das sir has shared also on group, I think. Okay, so up to this point, I just showed you how we see alpha. Okay, how we see alpha. I just showed you how we see alpha. Now we will see estimation. Okay, now we will come to the point about estimation. So what does estimation means? So first we will see the general definition of estimation. Okay, general definition of estimation. So what does estimation means in general? It is a rough calculation of the value, number, quantity or extent of something, right? We estimate it. A rough calculation of the value, number, quantity or extent of something. That is a general definition of estimation. Now we will see the statistical definition of estimation. What does it mean? It refers to the process by which one makes inference about a population based on information obtained from a sample. Okay, now you should go to my first class where I told you that there are two types of statistics, descriptive and inferential. And I also told you that when you are describing your sample data, that will be descriptive statistics, and when you are making an inference out of it, when you are making a conclusion out of it, that is inferential statistics. So here we will be actually making some inference out of it. Okay, I hope the definition of estimation is clear to you. Statistical estimation, so it refers to the process by which one makes inference about a population based on some information from sample. Now estimates are of two types. Estimate. Yes. Okay. Okay. I think by mistake someone's mic is on.
Yeah, same to you. Good. Yeah. You are busy.
I was in a meeting. All the things that can I.
Unmuted. Yes, so we will go ahead. Now estimates are of two types, point estimate and interval estimate. Now we will see one by one. What does a point estimate mean? As the name indicates, it is a point. So only one value I'll be showing. A point estimate of a population parameter is a single value. Okay, it is a single value. Example, the sample mean bar x is a point estimate of the population mean mu. Means I am only reporting my result in a single value. So it is a point estimate. But when I say interval estimate, I have to understand that I will be providing an interval with some level of confidence. An interval estimate is defined by two numbers between which a population parameter is set to lie. Let's say A less than bar x less than B. So A less than bar x less than B is an interval estimate of the population mean mu. Okay, so in point estimate, I will be giving a single value. In interval estimate, I will be giving two values between which my actual answer will lie. Okay, so that I can make a decision out of it. So I hope up to estimation it is clear to you. Arti Krishnan, are you there? Can you hear me? Arti? Now also 36 participants are there. Anyway, we'll be seeing that later. Gauri Krishna RM, you able to hear me? Gauri Krishna.
Yes, sir. Yes, sir.
Gauri Krishna, what is alpha?
Sir, alpha is the level of significance, or it is just the proportion of data, sir.
Okay,
So
proportion
with
of
that,
data.
yes, sir.
Okay, so suppose alpha is 0.50. What does it means?
Sir, sorry.
Suppose my alpha is 0.50. What does it means?
Sir, with the corresponding alpha value, we'll find the corresponding Z value. So first of all, we will take the level of significance, then we will divide it by 2, and then at last we will find out the corresponding Z value, sir.
Okay, okay. Mohan B, you able to hear me? Mohan? You able to hear me, Mohan?
Yes, sir.
Okay, but your voice is. Gopika ji, you able to hear me? Gopika?
Yes, sir. Sir.
Gopika?
Hello, sir. Hello, sir.
No, your voice is low.
Hello.
Adira, VC, able to hear me? Adira?
Yes, sir.
So Adira, can you define point estimate?
Yes. Point estimate is where the parameter actually it's a single value of the parameter, or the parameter lies within a single value, and and the interval estimate, the parameter lies within a range.
Okay. Okay. So we will move ahead. So up to this point, I just showed you um, the how we will interpret and how we will see the standard normal distribution, and I've also gave a brief of what does estimation means. Now we will go ahead with some examples. Okay, we'll see some examples of estimation now. So one thing you need to understand that I'll read the line. In most cases of applied interest, the data we have available will be only a small fraction of the total existing information on the subject. Okay, and quite rightly so. We are living in a very big world, so we cannot collect all the data all the time. And by now we are not advanced that much that full-time real-time data will be with us for statistics. So we will have a sample only, right? So we cannot be certain that the data we have will be a true representation of the existing situation. We cannot be sure always that whatever data I am collecting will be a true representation, right? Like I gave you example last time that professors in Stanford predicted that there are 90% chance that Hillary Clinton will become the president, but that time who became the president? Donald Trump, right? So we cannot claim that whatever sample data I am collecting is true representative of my whole population. So my job as a statistician or as a researcher is to see and is to optimize the maximum possible ways of obtaining an accurate answer from my process. Okay, of obtaining an accurate answer from my process. That is what my aim should be, and this is why these methods are in practice. So we'll take one example now. Example: suppose a distribution of citrus fruits wants to know the mean weight of California grapefruits. He wants to know the mean weight of California grapefruits for the purpose of estimating the shipping cost, because the shipping cost will be based on weight. Now, what will be the straightforward answer to it? We can weight each California grapefruit and find the average. But you yourself can think that lot of fruits, which is tedious and not at all feasible. So what we will do is that we will collect we will collect some samples out of it. Now, in this case also, you need to understand two things. There will be sample mean and there will be true mean. Okay, what is our job is, I told you already that our job is to make our sampling representative. Our sampling representative. That means our sample mean should be same as true mean, ideally, right? Our sample mean should be ideally same as true means. If not same, at least it should be near to true mean. That then only I will be able to draw inference for my population. Okay, so the gap, how we will fill by using inferential statistics. Okay, so what we will do, we will select a random sample of a relatively few grapefruits and calculate the mean of all the grapefruits in the sample. Okay, so what our job is that our job is to fill the gap between sample mean and true mean. Of course, there will be some error, but we have to minimize that error. Now, there are two things to it, and I already shared it with you already. If my sample number is more than 30, I will categorize as large sample, and for large sample, I can apply normal distribution. I can apply normal distribution. And if my sample size is less than 30, I will categorize as a small sample and I have to apply t distribution. Okay, I have to apply t distribution. So now I will slowly show you how we derive confidence interval. Because I have to report my mean, I have to report my true mean. But I told you already that when you are actually reporting something, it should be in the range. Like temperature, we always see paper, it is in range. Relative humidity is in range. Wind direction, wind speed, all these environmental meteorological parameters are in range. Then only we are able to make decisions out of it. So what we will develop is now confidence interval for mean. But while developing confidence interval for mean, we need to see the number of samples. So if it is greater than 30, it is a large sample. If it is less than 30, it is a small sample. Now, there are two approaches by which we can develop and procedure for estimation of true mean. There are two approaches. First one is the law of averages, also called the law of large number. The law of averages or law of large numbers. And the second one is the central limit theorem. One by one we'll see. So what does the law of averages says? It says that if a population is the true mean mu and bar x is the sample mean of a random sample of n members of a population, then as n grows larger and larger, okay, of course we are taking more samples, then the sample mean bar x become more closer to the mean. Okay, I hope population and sample, these terms are clear to you. So what does law of averages says that if you take more samples, the sample mean will be slightly moving towards the true mean, which is what our approach is. But we all know that full time we cannot take all samples, right? All the time I cannot take all members of the population in consideration. But still we will try to take more number of samples. So the law of averages says the more number of samples we take, the more closer our sample means move towards the true mean. Okay, this is law of averages. Second one is the central limit theorem. Central limit theorem actually is more practicable, practical when I'm applying statistics. So what does it says? It says that if a population has the true mean mu and the standard deviation sigma, okay, then the probability distribution of the set of all possible sample means of n members of the population becomes closer and closer to the normal distribution with mean mu and standard deviation sigma by root n. This is what you need to learn, sigma by root n, as n grows larger and larger. So if I am taking more samples, then my true mean will be my true mean will move towards the sigma by root n as n grows larger and larger. This you will understand why it is sigma by root n, because now we are going to develop one method. Okay, so I hope the law of averages and the central limit theorem is clear to you. Now on the left side, what you are seeing is a normal distribution, and on the right side, what you are seeing is normal distribution for Z scores. For Z scores, I hope this you know very well now. Z is bar x minus mu divided by sigma. But here you see, I have replaced sigma by root n. Okay, in last time when I took the class, in case of standard scores, we did bar x minus mu upon sigma. But here you see it is replaced by sigma by root n, because I have to take my sample more towards the true mean. Okay, more towards the true mean. So this is normal distribution. This is normal distribution for the Z scores. Now we will see this in terms of percentage points. So in terms of the percentage points of the normal distribution, this means that a fraction 1 minus alpha, or a percentage 1 minus alpha into 100%. If I multiply it by 100, it will be percentage 1 minus alpha, or a percentage 1 minus alpha into 100% of the Z scores fall between the numbers minus Z alpha by 2 and Z alpha by 2. I told you last time that why we are taking half, so that we can leave half on the minus side and we can leave half on the right side. Okay, we'll see one example. I hope this is clear to you. When I am taking a fraction of 1 minus alpha, or a percentage 1 minus alpha into 100%, so my Z score will fall between the number minus Z alpha by 2 and Z alpha by 2. This Z alpha by 2 I already showed you here. This is here, Z alpha by 2. I told you that time also that I am not considering minus sign here, because I will show you next time. So that minus sign has come now, minus 1.96 and plus 1.96, minus Z alpha by 2 and Z alpha by 2. So let's say example, I want to see my data on a level of significance of 5%. That means 5% of the time I can agree that there is an error, but 95% of the time my value should be correct. Okay, so let's say my alpha is 0.05 level of significance. So how much 1 minus alpha will be? 0.95, right? So I converted 0.95 to percentage, multiply by 100, it is 95%. It is 95%. So how do I interpret it? I interpret it like, in probability language, we can express this fact by saying that the probability is 95% that for any particular sample mean bar x, its Z score, this one, will fall between minus 1.96 and plus 1.96. I hope now you are able to understand why I did half. If I am fully taking alpha here, then here I leave full. This will be my answer, but no, we should not do it like it. Out of that alpha also, alpha by 2 we should leave on the plus side and alpha by 2 we should leave on the minus side, so that I can be more towards my true mean, right? That is what my point is. That is what my intention is. I have to move towards my true mean. I have to move towards my true mean, this line. So I did. So I did divide by. I divided my alpha in two parts. Alpha by 2 on the plus side and alpha by 2 on the minus side. So 1.96 minus 1.96. Okay. So I hope this is crystal clear to you that when we are taking any alpha, V2 alpha by 2 of it, and then we will take 1 minus Z alpha by 2 on the minus side and plus Z alpha by 2 on the right side. Okay, this is how we form confidence interval. Now, what is our limitation here? I am talking about percentage this and that, but here we don't know mu and sigma, right? Neither I know population mean, nor I know population standard deviation. But we do know that whatever it may be, my 95% data will be between minus 1.96 to plus 1.96. That is the beauty of statistics. When you already use some work which has been done by authors, or which has been and when you already know the well established principles, you may not be knowing anything, but you are slightly sure or up to 95% sure that my data will be within a z score of minus 1.96 to plus 1.96. Okay, I hope up to this point it is clear to you. We are deriving equation now. So if I see from algebra point of view, I should write that minus 1.96 on the left side, z will be in between, and plus 1.96 on the right side, right? Then now I have to replace my z from the formula. What I showed you last time, z equal to bar x minus mu divided by sigma. But I told you as per the central limit theorem that sigma to be replaced by sigma by square root of n. So I have replaced this. You can see here sigma by root n. So minus 1.56 less than bar x minus mu upon sigma by root n less than plus 1.96. Now to simplify it, what I will do, I will multiply both sides by sigma by root n. Sigma by root n. So minus 1.96 into sigma by root n. This should be less than, now since I have multiplied this denominator sigma by root n will be cancel out. So only numerator will remain of bar x minus mu. So minus 1.96 sigma by root n less than bar x minus mu less than plus 1.96 sigma by root n. Okay, but I want mu only. I want my mean only to be in the center. So I will send my x on the other side. Okay, on the other side. So here I have sent my x. So here it will be bar x minus 1.96 sigma by root n less than mu, which is less than bar x plus 1.96 sigma by root n. Okay, so here it will be minus, here it will be plus. I simply send my bar x on the other side. Okay, on the other side. So when I sent here, it became minus 1.96 sigma by root n minus bar x, and here it became 1.96 sigma by root n minus x. So minus myself can become plus. So this side it came plus, this side it came minus. So bar x minus 1.96 sigma by root n less than mu less than bar x plus 1.96 sigma by root n. So this is the definition of finding our true mean in confidence interval terms. Means I'll be reporting my answer in terms of interval. Okay, so in this equation, bar x is our sample mean based on our particular random sample of n numbers of the population. Sigma is our true standard deviation of the population, and n is number of data points in our sample. I hope this is crystal clear to you. Now we will again take that example of citrus grapefruit. I told you last time in the last substance slide. Suppose we try to estimate the true mean mu by selecting a sample of n equal to 64 grapefruits. I have collected 64 grapefruits. So we weight each of these grapefruit and they turn out to have a mean weight of 11.36 ounce. Okay, because the book I used to read was from US, so it is not in kg and grams, it is in ounces. So it turns out that mean weight is bar x equal to 11.36 ounces. Now we want to know how close we can expect our sample of 11.36 to the true mean. Okay, this is from a sample, right? I told you right from the start. This is from a sample, but I have to see how close this sample mean is to my true mean. Now we will apply our statistics here. Since the n is greater than 30, I will categorize it under large sample. Okay, large sample. So for large sample, we will put sample standard deviation is equal to sigma true standard deviation. When the sample is large, the sample standard deviation is equal to true standard deviation, that is sigma. So I'll see my formula. My formula was bar x minus 1.96 sigma by root n. So my bar x was 11.36. 1.96 I am seeing because I want to see on a level of significance of 5%. And sigma upon my n is 64. N is 64. So under root of 64 less than mu less than 11.36 plus 1.96 sigma by 64. Now sigma I know. Okay, sigma I know that it is 1.76 ounces. They have given standard deviation also. So I put 1.76. So we will calculate it 11.36 minus 1.96 into 1.76 by under root 64. It turns out to be 10.92. So what does it mean? It means that on the basis of our random sample of 64 California grapefruits, we can be 95% sure, that is where our confidence interval lies. We can be 95% sure that the true mean weight of all California grapefruits is somewhere between 10.92 and 11.80. Okay, now try to understand the other perspective. I told you that there are two types of estimate, point estimate and interval estimate. But point estimate, it is for sample, right? And I'm not able to say whether it is near to my true mean or not. And let's say if I'm able to say, I should know the degree of confidence I'm having on it. Okay, certain error I can allow. So I have allowed that, okay, 5% of the time I can be wrong. It is agreeable to me. But I should have 95% confidence interval. So for 95% confidence interval, my range is 10.92 and 11.80. So on the basis of our random sample of 64 California grapefruits, we can be 95% sure that the true mean weight of all California grapefruits is somewhere between 10.92 and 11.80. Now see the other angle also. The interval 10.92 to 11.80 is said to be a 95% confidence interval for mu. Okay, it is a 95% confidence interval for mu, and it allows us to come up with not only estimate of mu but also measure of how accurate we can expect our estimate to be. Right? We have estimated, but how accurate is our estimate to be, that also we can see with this one. Okay, so here you can see this is the center 11.36. And I can go next 0.44 up to 10.92, and I can go right 0.44 up to 11.90. So my true mean will be in this only. Okay, I hope this is clear to you. Now we can generalize this formula for any level of significance. Last example was for 5%. So how I can generalize that 1.96 I can replace with z alpha by 2. So bar x minus z alpha by 2 s by root n less than mu less than bar x plus z alpha by 2 s by root n. Okay, so here what we can do is that for different degree of confidence I have calculated all these things. So starting with 80%, let's say, yes. So suppose I want to start with 80%. I want to start with 80%. So 1 minus alpha is 80%. So of course alpha will be 0.20 only. Then only this is 80%. So alpha by 2 is 0.10. With this 0.10 from table A3, I know that z score will be 1.28. Right? Then if it is 1.28, my z alpha by 2 is by under root n will be 0.28. 0.28. And with that, what I can do is that we can calculate the 11.08 less than mu less than 11.64. Okay, similarly 90%, 95%, 98, 99, 99.9. Okay, so I hope up to this point it is crystal clear to you how we will go. This s by root n I have taken for the California grapefruits only. This s by root n will vary for each thing. Okay, you have to keep this in mind. It is not fixed. Now this table is for California grapefruit example only. So I hope up to this point the generalization of confidence interval for any level of significance is clear to you. And the same I can represent graphically. 11.36, 80%, this one 11.02. If it is 90%, this one. If it is 95%, this one. Now I want you to observe one thing. You yourself see, when my degree of confidence is less, when it is less, let's say 80%, my range is also less. And when my degree of confidence is more, my range is also more. You observe one thing, because when I want to say something confidently, I'll try to make it more generalized. So as my confidence interval is increasing, my range is also increasing. But in standard convention of statistics, we usually go with 95% confidence interval. And I'm sure you all are PhD student by now. You would have seen many times that alpha was taken 0.05 in some of your, when you are doing some literature review, the level of significance alpha was 0.05. So it is 95% only, that it is with the 95% confidence I have commented that. So this is graphical representation of table 2. Now we'll take one example. A random sample of 100 private automobiles registered in the province of Ontario put a mean yearly mileage of 6,500 on their odometers with a standard deviation of 1400 miles. These facts were brought out as a part of a statistical study of automobile usage commissioned by a local insurance agency. Find a 99% confidence interval for the true mean yearly mileage of all private cars in the province of Ontario. Okay, the question is, they have taken a random sample of 100 private automobile which were registered in the province of Ontario. And the mean yearly mileage of those cars was 6,500 on their odometers with a standard deviation of 1400 miles, the distance. So they want us to find, because they have taken 100 sample only, they have survey 100 cars only, but they have to generalize the result for the province of Ontario, for the whole province of Ontario, for all the car owners. So our question is, find a 99% confidence interval for the true mean yearly mileage of all private cars in the province. So let's start one by one. For a 99% confidence interval, my 1 minus alpha 100% will be 99%, right? So 1 minus alpha will be 0.99. So I'll keep alpha this side and send 1 there. So minus 1 minus 0.99, that will be 1 minus 0.99. So my alpha is 0.01, but I have to do alpha by 2. So my alpha by 2 is 0.005. So for 0.005, my Z will be 2.57 from the table. We can see from table A3. 0.005. 1 second. One second. Something like that. So 0.005. So it is between 0.0049 and 0.0051. So it is up to us. Last time also someone asked. That time I said that either you can take the previous one or the next one also. If you want to go more accurate, you can take average also. Okay. So it is 2.57. In that case, they have taken the previous one. And I told you that time that we will not consider the sign of the number, because anyway we are going for the interval. So my Z alpha by 2 is 2.57. Now N is 100. My bar X is 6.500 miles, which we have taken, and AC is 1.00. I'll put all these things in my formula. Bar X is this, Z alpha by 2 is 2.57, S upon bar N is 1400 by under root 100. Less than mu, less than this. 6140 less than mu, less than 6860. Therefore, we can be 99% sure that the true mean yearly mileage of all private cars in the province of Ontario lies between 6140 and 6860 miles. So I hope you are getting what I am trying to show you. I am trying to show you that even with a small number of samples, we can very well generalize it for the population based on some inferential statistics. Okay. Now, what if our sample is small? What if our sample is less than 30? In those cases, we will use T distribution. Okay, we will use T distribution. So one thing is that Mathematical calculation show that if the overall population from which a random sample is selected as the normal distribution, then for all sample of size n, no matter how large or small, the number will have t distribution also. Means anyway, if the number is large, I can put t distribution, but if it is small, for sure I have to put t distribution. So t is equals to bar x minus mu divided by s upon root n. And this is the formula for t distribution. For z, it was sigma and bar x. For t, it is mu and s. So bar x sample mean, capital S sample standard deviation, and small n number of data points in the sample, and mu is our true mean of population. So bar x minus t alpha by 2 n minus 1 s by root n less than mu bar x plus t alpha by 2 n minus 1 s by root n. Okay, this is the minus side and this is the plus side. And here n minus 1 is what? N minus 1 is our degree of freedom. That I'll show you what does it means. N minus 1 is our degree of freedom. So instead of z alpha by 2, I am taking t alpha by 2 n minus 1. Rest formula is same. And sigma is replaced by s. Okay. Now, question number 2. A corporation which maintains a large fleet of company cars for the use of its sales staff needs to determine the average number of miles driven monthly per salesperson. Number of miles driven monthly per salesperson. A random sample of 16 monthly car use records was examined, yielding the information that the 16 salesperson under study had driven a mean of 2250 miles. Sorry, mean of 2250 miles with a standard deviation of 420 miles. Find a 95% confidence interval for the true mean monthly number of miles per salesperson for the entire sales staff. Okay, so I hope question is clear to you that a corporation which maintains a large fleet of company needs to determine the average number of miles driven monthly per salesperson, and they have did some statistics and they have interviewed 16 salesperson and they found that mean distance is 2250 miles and standard deviation is 420 miles. Now they want to generalize this result with a 95% confidence interval for the true monthly number of miles per salesperson for the entire sales staff. Now one thing we have to keep here in mind is that since it is 16, it is less than 30, we will, instead of normal distribution, we will apply t distribution. So our n is 16, bar x is 2250, s is 420. Now since n is less than 30, we will use the percentage points of t distribution. Okay, so we want a 95% confidence interval, right? So my alpha will be 0.05. Naturally alpha by 2 will be 0.025. So degree of freedom is n minus 1. Always remember that degree of freedom is n minus 1. This we'll discuss sometimes. N minus 1. So my samples were 16. So my degree of freedom is n minus 1, 15. Okay. T alpha by 2 n minus 1. Now for t distribution there is a separate table in this. Okay, there is a separate table in this. Here I will write my alpha to the subscript t 0.10, t 0.050, t 0.025, and here it will be degree of freedom. Instead of z score there will be degree of freedom, and it will be up to 29 and 30 only, because above 30 we will not use t distribution, right? Above 30 I will not use t distribution. So it is up to 1 to 30 only. So here my degree of freedom is 15 and my confidence interval is 0.025. So I'll go in the table and I'll see t 0.025 is the column I should look upon, and my degree of freedom is 15. So I will see on the 15th row of degree of freedom in t 0.025. So it is 2.131. It is 2.131. T 0.025 15 2.131. So you can see here t 0.025 15 2.131. Now I'll put these values in my t distribution formula. 2250 minus 2.131 into 420 by root 16, because my sample is 16, less than u less than this full term. So what I will conclude is that therefore we can be 95% sure that the true mean monthly number of miles driven per salesperson for the entire sales staff is somewhere between 2062.2 and 2473.8 miles. Okay, and the average was 2250 only. Of course, it will be in between then. So when the number of samples were less, even I could generalize it for my whole population. Okay, I hope this is clear to you. Now one more example we'll take. Question number 3. Because pharmaceutical companies manufacture antibiotics in large vat for later bottling in smaller units, it is necessary to test potency levels at several locations in the vats before bottling. Okay, before I am putting it in bottle, we have to see the potency level. While it is impossible to achieve complete uniformity in potency levels of the bottle product, such testing is required for the purpose of obtaining the mean potency level of the entire batch. Okay, you would have seen in many tablets, suppose multivitamins, you may be taking, let's say, 2.2 mcg of methylcobalamin. Methylcobalamin is vitamin B12 basically. You may be taking 2.2 mcg, but in your body that may not be fully absorbing in that. Of course, some bioavailability factors are there, but apart from that, the content of capsule also depend on the potency of that chemical in that capsule. Okay, so that is why it is required. So in one such test, the readings at 12 randomly selected location in the weight were 8.9, 9.0, 9.1 and so on. This they have given potency levels out of 10. Now we want find the 98% confidence interval for the true mean potency reading for the entire batch. Okay, for the entire batch. So first what we will do, we will arrange our data, then we will find out mean of it. The mean is 9. Okay, mean is 9. Then we will calculate this term x minus bar x. Then we will calculate this term x minus bar x square, and we will find the standard deviation 0.14 divided by total number of samples, 11. Actually it is 12, but in denominator we take n minus 1. So 12 minus 1 is 11. So it is 0.113. Okay, 0.113. So since we want a 98% confidence interval, alpha is 0.02, alpha by 2 is 0.01. Right, I divided by 2 only. First I divided 100 minus 98, it is 2%. Then if it is in percentage, I converted it to fractions, 2 by 100, 0.02. And alpha by 2 is 0.01. So the degree of freedom df is 12 minus 1, which is equals to 11. I told you it is n minus 1. So now my nomenclature will be t 0.01, 11 I have to see. T alpha by 2 n minus 1. Now I'll go to my t distribution table and it is t 0.01. T 0.01, it is here. T 0.01 and my degree of freedom is 11, right? So this is 11 and this is this column 2.718. My t 0.01, 11 will be 2.78. So 9 minus 2.718 and this AC is 0.113. 0.113 divided by under root 12 less than this. So 8.91 less than mu less than 9.09. So we can therefore be 98% sure that the true mean potency level of the entire batch of antibiotics in the vat falls between 8.91 to 9.09. At least it is not below 8.91. It is not below 8.91. Okay, so this is how we report results for samples less than 30 and for a confidence interval. Okay. Now, choosing the sample size. Actually, one thing you need to keep in mind that there are two ways to a particular thing. A few days before, one student came to me. She was asking about the sampling of bananas. She was collecting sample from different region of Kerala, and she's trying to work out the impact of pesticides or the any change if it is happening. So, see, there are two ways. Either you can do your work and then later on you can come to know that, oh, I should have collected more samples so that my error would be below 5%. Or you can do reverse also. Before and itself, you can have your error in your mind that, okay, I will only allow, let's say, 2%, 3% or 5% of the error. Now to obtain my error below 5%, what should be the number of sample size? So this we can do with this formula E equal to Z alpha by 2 S by root n. So you can see here it is similar to the term what we are reading in confidence interval. So it is naturally a different way only. So we can be 1 minus alpha 100% sure that the maximum possible error in using bar x as an estimate of mu cannot exceed E. Here we will limit E. So technically the two procedures, confidence interval and error of estimation, are merely ways of viewing the same information from two different vantage points. Okay, in one I have started and I have calculated the error. In the other one, first I have kept the error in my mind and then I have started my sampling. Okay, so we can be 1 minus alpha 100% sure that the maximum possible error in using bar x as an estimate of mu cannot exceed e. Okay, now we will see one example. Okay, suppose my population standard deviation I can give up to 1.76 and my sample size is like this, n is 3664. This is just a table only for a 95% confidence interval for the true mean of a population having a standard deviation of 1.76, 36, 64, 100 and so on. So of course my z alpha by 2 will be 1.96. I have already said 95% is my confidence interval. My standard deviation is also fixed. So here with this two, I can see the error. So you see, when the number of sample is less, error is more. Just 1 minute. Hello? Shravan. Yeah, so you can see here that when my sample size is less, my error is more. As sample size is increasing, error is decreasing. Yeah, the error is getting minimized. Okay, error is getting minimized. Now we will see one example. Question number 4. So, one second. So, particular owners of a chain of coin-operated beverage machine advertise that their machines dispense on the average 7 ounces of soft drink per cup. In foreign, actually, from last 30-40 years before itself, they have automatic vending machines. Okay, so this is related to that only. So owners of a chain of coin-operated beverage machine advertise that their machines dispense, on the average, 7 ounces of soft drink per cup. A consumer testing organization is interested in the question of whether a particular machine is meeting its specification. They have some specifications. It wants to run a study after which it can be 95% sure of having the true mean amount dispensed by the machine correctly, estimated to within an error of 0.01 ounce. Now here you see, here itself we want to minimize within 0.01 ounce. So if a preliminary analysis indicates that the amount dispensed have standard deviation of 0.12 ounce, how many sample cupfuls, cupfuls does the organization need to measure in order to achieve the desired level of accuracy? Now, instead of first measuring and then calculating, now they have fixed the error and now they will take the cups. Okay, sample. So the acceptable level of error is E 0.01 and desired degree of confidence is 95. So therefore, alpha will be 0.05 of course, and alpha by 2 will be 0.025. So that Z alpha by 2 0.025 is 1.96. This is standard. 1.96 for 95% interval is standard. So I will put in my formula E equal to Z standard deviation by root n. N I don't know. N I have to calculate the n. I have to calculate the sample size. So 0.01, 1.96 this under root n, 1.96 0.12 divided by 0.01. So bar n equal to 23.52. I did square of it and n equal to 554. So to achieve the desired level of accuracy, then would require at least 554 data points samples. 554 data points, and you very well know that if I increase this error, sample size will reduce. Now if I do it 5%, then it will be reduced. Okay, so I hope this is crystal clear to you now that if the error is less, sample size will be more, and if the error is more, sample size will be less. Last question. A new drug for alleviating mental depression is proposed and we want to estimate its effectiveness. Okay, there is a drug for alleviating mental depression. And if you want to be 98% sure of having the true proportion of patients helped by the drug correctly, estimated to within 0.03, how many patients do we need for our study? Okay, given standard deviation is 0.5. Okay, so here you need to understand that they have created one new drug for alleviating mental depression and they want to measure its effectiveness. Let's say they want 98% confidence interval. 98% confidence interval. If you want to be 98% sure of having the true proportion of patients helped by the drug correctly, estimated to within 0.03. How many patients do we need for our study? And given our S is 0.5. So here error they have limit to 0.03. Here error they have limit to 0.03. So here alpha is 0.02, then I will do z alpha by 2, z 0.01 equal to 2.33. E is 0.03. E I put 0.03, standard deviation 0.5, bar and we need to calculate, and 2.33 we came to know from our value of alpha. So if I calculate, it will be n equal to 1508. Therefore, a sample of 1508 patients will be sufficient to guarantee the level of accuracy desired in our study of the drug effectiveness. On the basis of sample of that size, we can be 98% sure of having the true proportion of patients have correctly estimated to within 0.03. 0.03 does not have any unit but a particular measure of them. Okay. So I hope this is clear to you. Now time for attendance, and anyone, any doubt? Anyone, any doubt?
Saurav,
Yes, sir.
what's the logic of taking alpha by 2
Yes, sir.
for
I'll
confidence
just,
level? We could have taken directly alpha.
yes, I will show you. Sir, you able to see screen?
Yes.
Sir, okay, first I'll show you this one. Sir, you remember that when we work in normal distribution, the proportion whatever we declare, it will be on the right side of the distribution, and remaining will be our
Correct.
1 minus whatever it is. This is the standard convention. But but when we are actually reporting the result, and if I'm only considering this one, I may include some outlier on the negative side. So what I will do, I will divide that in, and here also, yeah, before that, here also you can see in the normal distribution table also, this area I am leaving, but this full hatchet area I am taking. So instead of leaving this side only alpha, I will left alpha by 2 on the both side. So what I did, instead of taking 5% on the right side only, I concept note, I left 2.5 on both. So that is alpha by 2. So this is the reason, sir, we take by 2.
But there again, outlier is included.
No, sir, included. It is not included, it is excluded. This one, when I'm taking this, I'm not considering this area, only the hatchet area I'm reporting. So I have excluded this one plus this one both, and I'm taking the more reasonable value. This one. Anyone else? Anyone else? Any question? Okay, if no further question, I declare this class is over, and I'll convey you the time of the last class, and then we will have exam. Okay, have a nice day.
Thank you, sir.
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 Welcome.